Hi, my name is Jolie Stokes. I'm Smith Physics 2212 Lab 2 on lines of charge. In this lab, we use GlowScript to produce computational models of charge, revisit ideas about point charges, and apply the ideas in electric fields on charges of tape. Using the results of our previous lab involving charge tapes, we would now like to measure the amount of charge on each tape required to cause two tapes to float above one another. However, this time, instead of modeling the tapes as a single point charge, we will model them as multiple point charges, also called a line of charge. Here are some fundamental principles to keep in mind. Coulomb's law states that F equals 1 over 4 pi epsilon naught times the charge of 1 times the charge of 2 over r squared. We'll also revisit Newton's second law, which states that force equals mass times acceleration, and superposition, which states that the net electric field equals all electric field sum. We'll first revisit the results from Lab 1. We found that the charge at a point charge of an electric tape was 1.137 times 10 to the negative 8th coulombs. We also found the force of gravity is equal to the negative force of the electric field at the floating distance. In our new lab, we found that the force of gravity is equal to 3.935 times 10 to the negative 4th. We also found that the force of the electric field was equal to 1.864 times 10 to the negative 3. We found that the charge on tape based off lines of charge was 1.107 times 10 to the negative 8th coulombs. We'll now look at the code in our GlowScript model. First, we'll look at the physical constants. Phys is 1 over 4 pi epsilon naught, which is equal to 9 times 10 to the 9th. Gravity is 9.81 meters per second squared, and we also have our mass and our estimated charge on the tape. Here we defined a function to create an electric field, and here we defined a function to create a line of charge. Next, we modeled two tapes, a top tape and a bottom tape, and we also calculated our electric field and our electric force. We created the force of the net electric field on the top tape, as well as the force of the net electric field on the bottom tape. Then, we created arrows to show these. We made arrows to show the net electric field and the gravitational force on the top tape. We also used the electric force vector and a gravitational force vector. Print the magnitude of electric force and the magnitude of gravitational force, and we were finished. This is what our model looked like. As you can see, we had the magnitude of electric force at 3.9 times 10 to the negative 4th. We also had the gravitational force at 1.86 times 10 to the negative 3. To conclude, we'll answer our what-if questions and gain a better understanding about the calculations we used for this model. First, what if we had modeled each of our tapes as a single point charge like in the previous lab? When modeling an object as a point charge, we're calculating the approximation of an electric charge of an object at a single location. However, modeling an object as many point charges that are averaged together, we're able to produce results that are more accurate to the true value of the object. Below are my calculations for the charge using 50 points instead of a single point. We can compare it to the results of the charge, modeling an object only using one point of charge. As we can see, when we use multiple points of charge, the number gradually gets smaller and smaller. If I'd used 100, it probably would have been even smaller, which means that it would have been closer to our exact value. Which brings us into our next question. Why do these estimates differ? Which value is more likely to be closer to the real value, and why? Our estimates will differ for the single point charge because we're calculating the electric charge at one location. However, for the line of charge model, we're averaging a bunch of electric charges across the tape. This means that our model is more likely to be closer to the real value, which also means that the more point charges we add to this model, the closer the resulting electric charge will be to the real value. To conclude the lab report, we'll discuss the possible sources of error that may have resulted in discrepancies in the results of our lab. So possible sources of error may have come from touching the tape with our hands that may have caused a loss in charge. The weight of the tape was calculated as a fraction of the mass of the roll of tape rather than being weighed on an actual scale. The tape is not actually a point charge. There are many charges acting on one portion of the tape at once, but we use point charges to simplify the system. We also did not account for outside charges, and the charges of the tapes were likely not equal